Bristles sharper than needles, paddle-like limbs rippling across unknown bodies. Most people think of earthworms as harmless, but underwater their relatives evolved alien hardware, thousands of body types, and behaviors built for sudden predatory strikes. Why do aquatic worms unnerve us more than their land-dwelling cousins? The reason is stranger and more revealing than you think. Segment by segment, the anatomy of an aquatic worm reveals a world built for survival in water. Along each side, fleshy paddles called parapodia jut outward, one pair for every body ring. These parapodia aren't soft or shapeless. They're packed with muscle fibers, bending and flexing with precision. Each paddle bristles with bundles of chitin-based spines that can range from barely 1/10 of a millimeter to nearly 3 millimeters in length. Under magnification, these bristles look more like glass needles or serrated wires than anything from a garden. Some polychaetes sport hundreds of kata on a single segment, clustered in tight fascicles, each one angled for grip, defense, or thrust. The structure is more than just decoration. Parapodia act as limbs and lungs, waving to push water past their gills or to anchor the worm against rocks and sand. The bristles themselves come in a dizzying variety, hooked, feathered, blade-like, each adapted to a specific niche. In species that swim, broad parapodia flare out like oars, catching currents, and in burrowers they flatten into ridges for tunneling through silt. The effect is a living machine, a modular body plan that can be rebuilt for speed, armor, or camouflage. Marine biologists like Greg Rouse describe these bristles as evolutionary armor. Thousands of species have refined their cheta into tools for survival, making aquatic worms look and move like something engineered for another planet. This alien hardware, visible only under close scrutiny, is the first clue to why aquatic worms unsettle us in ways their land-based relatives never do. Across the world's oceans, the sheer variety of aquatic worm shapes defies easy comparison to the humble earthworm. Polychaetes alone count around 12,000 described species, each with a body plan that seems custom-built for a different corner of the sea. Some, like scale worms, carry overlapping plates that shimmer with iridescence, giving them the look of armored centipedes from another world. Fireworms, on the other hand, are lined with vivid tufts of stinging bristles, warning would-be predators with neon reds and whites. The bootlace worm, a ribbon-thin marvel, can reach lengths of up to 50 meters, longer than a blue whale. Yet it slips unseen through kelp forests and tide pools. Color is another realm where aquatic worms break the mold. Where earthworms are muted in shades of brown and pink, marine species flash metallic blues, greens, and even ultraviolet, thanks to specialized pigments and light-reflecting structures in their skin. These colors can signal danger, camouflage among corals, or dazzle in the open water, making identification a challenge even for experts. Size and shape stretch from the compact, almost invisible threadworms that weave through sand grains to the massive muscular predators lurking in deep-sea mud. The Cambrian explosion, over 500 million years ago, set this diversity in motion, launching evolutionary experiments that continue today. For every earthworm's familiar, uniform tube, the ocean offers a parade of spined, plated, and ribboned forms, each one pushing the limits of what a worm can be. This spectrum of shapes and sizes lays the groundwork for the movement and behaviors that make aquatic worms so visually unsettling. Water changes everything about how a worm moves. In the lab, high-speed cameras and flow tanks reveal just how much force these animals can generate. Polychaetes, when swimming with their parapodia, push against the water with a thrust that clocks in around 0.5 Newton, remarkable for a creature that rarely tops 20 centimeters in length. At a steady pace, they cruise at about 0.3 meters per second, gliding through the water far faster than any earthworm can crawl through soil. But when startled or on the hunt, some species unleash a burst of speed, reaching up to 1.2 meters per second. That is the kind of velocity that makes their movement look sudden, almost violent. And it is a world apart from the slow, inching progress of their terrestrial cousins. Professor Michael Smith's flume experiments show how parapodia beat in rapid, coordinated waves, each stroke sending a pulse of water backward and launching the worm forward. The bristles don't just provide grip, they slice through water, reducing drag and channeling thrust. Motion tracking reveals a rhythm that is both hypnotic and unpredictable, with segments flexing out of phase to create a rolling serpentine motion. In open water, this translates to a creature that can change direction in a flash, darting between rocks or disappearing into silt in a fraction of a second. These numbers aren't just trivia. They explain why aquatic worms seem so much more alive and so much harder to anticipate than the familiar earthworm. The physics of water let them turn their bodies into engines, multiplying the impact of every twitch and undulation. For predators, or for anything unlucky enough to cross their path, that speed is the difference between escape and capture. Buried beneath the sand, the bobbit worm waits in perfect stillness. Only a few antennae break the surface, tuned to the faintest vibrations in the water. Here, physics is on its side. The surrounding sediment masks its body, while the low drag of water lets it remain almost invisible until the moment comes. Unlike earthworms, which crawl at a slow 0.02 meters per second, the bobbit worm can explode into action at nearly 2 meters per second. Its strike is powered by a body designed for sudden violence. Muscles coil and release, sending the worm upward in a flash. The jaws themselves are formidable, scissor-like mandibles stretching up to 4 centimeters, snapping shut in just 0.02 of a second. Marine engineers describe these attacks in terms of Reynolds number, a measure of how fluids behave around moving bodies. In the bobbit worm's world, the Reynolds number sits around 150, a range where water flow is neither perfectly smooth nor completely chaotic. This gives the worm a unique advantage. Its body cuts through the water with minimal resistance, while the sand muffles any warning. For prey, there is almost no time to react. This blend of stealth and speed is rare among worms. Most earthworms spend their lives hidden in soil, their slow, rhythmic movements barely noticeable. The bobbit worm, by contrast, is a master of ambush. Its entire anatomy is tuned for the split-second moment when a fish or crustacean comes too close. In a single fluid motion, the jaws snap shut, dragging the victim below. The violence is over before the silt has time to settle. The mechanics behind these strikes, unseen, precise, and relentless, set the stage for a kind of biological horror that feels more like a nightmare than a natural event. Leeches have perfected the art of feeding without detection. When a leech attaches to its host, it releases a cocktail of chemicals through its saliva. The most potent of these is hirudin, a peptide that binds to thrombin with an affinity measured at nearly 1 billion per mole. This shuts down the body's ability to clot blood, allowing the leech to draw a meal uninterrupted. In a single feeding, a leech can take in up to 5 times its own weight, swelling as it siphons blood through specialized suckers. Dr. Amina El-Sayed, a molecular biologist, describes hirudin as a molecular lockpick, engineered by evolution to slip past the body's defenses. The same compound that makes leeches unsettling in the wild has found a place in medicine, used to keep blood flowing in delicate surgeries. But in the water, this invisible chemistry turns a simple parasite into something that feels invasive on a cellular level. In the deep ocean, darkness stretches for miles. Here, life hides in the silt and shadows, waiting for the right moment to reveal itself. During a NOAA survey, a remote vehicle hovered above a patch of empty seabed until, in less than half a second, a cluster of bristleworms erupted from the mud, blanketing the camera's view. These eruptions can involve thousands of individuals at once, forming moving carpets that ripple across the seafloor. More than 2,000 species of polychaetes have been documented below 2,000 meters, many thriving around hydrothermal vents where entire colonies blanket the rocks. The scale of these gatherings is hard to imagine. Vent communities can stretch for meters, with worms packed side by side, each adapted to survive in total darkness and toxic chemicals. In these depths, the ocean keeps its secrets until, in a flash, the hidden becomes impossible to ignore. Right now, aquatic worms shape the health of rivers, reefs, and even our food chains, often unseen, but essential. Their strange forms are reminders that life's most vital work often happens out of sight. Sometimes, the things we fear most are just doing nature's heavy lifting. Share your thoughts below.